All right, so let's work this problem. We've got a frame, pretty simple frame, cantilever frame. So it's fixed connected here at A and fixed connected here at B. And I want to find the horizontal displacement at point C. So the first thing, I'm going to use virtual work. So what I want to do first is find moment expressions in these two segments, right, as a function of the real loads. So let's do that first. I'm going to start with section CD because that's the easiest one to do. So imagine, if you will, that we cut the section somewhere like this. Do you want to work this cantilever piece or this L shape with the fixed connection? I think you can tell by my tone of voice that that would be a bad choice. You probably want to work this little simpler. I don't need my reactions, and it's a lot less to deal with. And I'm going to assume that that coordinate is vertical, and we'll say that's, we'll call that Y. So let's do section CB. So I'll draw that little free body diagram, and I will assume that we have a dimension going up of value Y. I have a distributed load acting in the horizontal direction of 200 pounds per foot. I can convert that into a concentrated equivalent, which would be the area under that rectangle, which is base Y times height. So that becomes a force of 200 Y. And the distance here to the cut is Y over 2. And then I'm going to assume that my moment in CB is in that direction. We're not going to account for axial force, and we're not going to account for shear force right now in our calculation. We're just going to do the bending part. So all I have to do is what? Sum moments at the cut. So I'll assume that I have a positive sign convention using right-hand rule. So I'm going to sum moments at this cut that I made and make sure it's in equilibrium. So when I do that, at the cut itself, I have the moment that I'm looking for, CB. What kind of moment does this create? Positive or negative? Negative. So that'd be minus 200 Y times a moment arm of Y over 2. So the moment, the real moment in this section CB is going to be 100 Y squared. That's not so bad. Now let's imagine a section somewhere here. By the way, I'll just make a note that we worked this way. So now I'm going to cut here. Do you want to work this L shape or this shape to the left? I'm going to go right. Why? I don't have to find reactions if I go right. If I go left, I got to go get these reactions. So I got to stop, go back, find the moment, shear, axial force there. I don't want to do that. All I have to do over here is get this little piece, and this I can resolve into a component. You can go either way, but I'm going to decide that when I do this section, I'm going to go from B to A. And I think you'll see it's not as bad as it looks. There's that section. I know this part is 8 feet tall, and I'm going to assume that my direction X, I'll call it X1, goes in that direction. And then I'll have the internal moment there, and this will be the moment in BA. Now, first off, I can find the concentrated equivalent force of this whole load on the left side, the right side. And that would be the area under this curve, which is a base of 8 and a height of 200. So what is that, 1,600 pounds? X halfway, so that would be at 4 feet. And then I'll have this piece of the distributed load. It has an intensity of 400 pounds per foot. So the concentrated equivalent force that acts through that centroid is again this area, which is the base, which I called x1, and the height 400. So this will be a value of 400 x1. And what's the distance from the cut? X1 divided by 2. So now I can sum moments again about the cut. Make sure I have an equilibrium. And what do I get? Well, starting here at the cut, what kind of moment is that? Positive or negative? Negative. So I'm going to have negative BA, moment at BA. This 400 x1 force, what kind of moment does that create about the cut? Negative. So the force is 400 x1 times a moment arm of x1 over 2. What about the moment about the cut created by this 1,600 pound force? Also negative. That'll be the force 1,600 times 4. So what is the moment at BA? Well, I'll put this to the other side. So it looks like it's minus 200 x1 squared, and that's 6,400. Is that right? 1,600 times 4? So there's my real moment. So what do we do next? This is called virtual work, so we have to do our virtual system. So what does the virtual system look like? Well, the problem is asking for horizontal displacement at C. So I'm now going to be looking at my structure. A, B, C. So I'm now going to apply a horizontal force at C. And I'm going to assume that it goes in this direction. And that is an assumption, but I'm just looking at the way the load is acting to the left and acting down. I think C is going to swing this way. So I'm just going to assume that's the way it's going. So any questions about that? About finding the virtual system? Now, since I chose this kind of free body and these directions for my moments and these coordinates, once you make that choice, you're stuck with it. So I got to use the same system for the virtual. So I'm going to come over here, and now for my virtual system, I have to do the same thing. So I'm going to go look at the same section from C to B. I'm going to draw the same free body diagram with the same dimension. I'm assuming y-axis up. I'm assuming that I had a moment that looked like this, except now it's the virtual moment in CB. That's the lowercase. And the only load on this structure is my virtual load of 1. So I just need to find the moment in that. I think if you look at that, that doesn't look too challenging. So if I sum moments, I'll assume right-hand rule for my sign convention. I'm going to sum moments at the cut and make sure I'm at 0. So when I do that, I have the internal moment, which is positive, the virtual moment at CB. And then the only other force on the system is the unit load, which creates negative moment with a moment arm of y. So it looks like my virtual moment CB is simply just equal to y. not so bad. Then I'll come down and do the next section, which I defined already as section BA. And again, I'll use the same situation, so I will sketch my free body diagram of BA. It was 8 feet. I assumed my coordinate acting from right to left was called x1. I assumed the moment in the same direction that I assumed here, except this one is the moment in BA, the virtual moment in BA. And the only load on the system, my horizontal force at C. So let's sum moments here. Again, right-hand rule for my sign convention, I'm summing moments about this cut that I just made, making sure it's in equilibrium. So when I do that, I have my internal moment, which is what? Positive or negative? That is negative. So my virtual moment at BA, what's the moment created by the cut by the 1 force? Positive or negative? Negative. And that will have a value of 1. And what's the moment arm? 8 feet. So it looks like the virtual moment in BA is negative 8. So really the hard work is done. Remember that now all I have to do is integrate the first segment, C to D, or C to B, C to B, and what's the length of C to B? 8. So I'm going to go 0 to 8 of the real moment in CB times the virtual moment in CB. I'm going to divide that by E and I, and that is integrated in the dy direction. And then I'm going to add to that section BA. We're going from B to A is 10. So that'll be an integral from 0 to 10 of the real moment in BA times the virtual moment in BA divided by its value of E and I. And that's integrated dx1. I just have to put these values in those positions, do the integration, evaluate it, answer. In this case, I didn't give you a value for EI, I just said it was constant. That's really all I need for you to do on the exam, is to correctly diagnose the problem, make your choices for moments, be consistent when you go to the virtual system, and then put them into this form, and you're done. And again, like we mentioned before, I probably won't require you to actually do the integration, evaluate, come up with an answer. But you'll notice that in frames, a lot of times, the limits of the integral are not that difficult to do. So there may be a situation where it's not that bad, so I may ask you to go ahead and go all the way. So when you're preparing for the exam, at least, do a few of them. I think mastering engineering is requiring you to go all the way. But for me on the exam, this is good enough. So, any questions? Okay.